Ever toss a plastic bottle in the recycling bin and wonder if it actually ends up, well, recycled?
It's a question we all have, and it highlights the huge challenge we face with plastic waste.
UGE doesn't even begin to cover it. We're talking about mountains of the stuff. Did you know that globally we churn out over 300 million tons of plastic waste every year? It's staggering.
Staggering and unsustainable. We can't keep burying our heads in the sand, or rather, burying plastic in landfills.
Exactly. We need solutions. And that's where things get exciting. Today we're diving into a potential game changer, catalytic pyrolysis.
Turning trash into treasure. It sounds almost too good to be true, right?
It does. But this isn't science fiction. We're digging into a real scientific paper published in Frontiers in Energy Research. These researchers explored how we can use heat and special catalysts to break down plastics, those very plastics we struggle to recycle, and transform them into valuable fuel.
And not just any fuel. We're talking about fuel with the potential to power our cars and industries.
And this paper has a fascinating twist. They use a naturally occurring catalyst found in, wait for it, Saudi Arabia.
Saudi Arabia.
That's-
That's not exactly the first place that springs to mind when you think of cutting-edge recycling technology.
I know, right? But it turns out Saudi Arabia is rich in a mineral called zeolite, which plays a key role in this whole pyrolysis process. But before we dive into the nitty-gritty of this research, let's break down what zeolite is and why finding it naturally is such a big deal.
So zeolite. It's a naturally occurring mineral with a really unique structure. Imagine a microscopic sponge riddled with tiny pores and channels. That's zeolite. And these pores are what make it so special.
Okay, I'm picturing this microscopic sponge. What makes these pores so important?
These pores act like traps, grabbing onto other molecules and holding them in place. This is crucial in catalytic pyrolysis because it brings the plastic molecules and the catalyst into close contact, allowing the chemical reaction, the breakdown of plastic, to occur more easily.
So it's like zeolite sets the stage for the plastic to break down more efficiently.
Precisely. And here's why finding a natural source of zeolite is a game changer. Traditionally, catalysts used in industrial processes are often synthetic, meaning they're created in labs using complex and often environmentally taxing processes.
So finding a natural alternative is a win for sustainability.
Absolutely. Using natural zeolite reduces the need for those energy-intensive synthetic processes, making it a greener alternative right off the bat.
It's like nature's giving us a helping hand, providing a readily available material to tackle this plastic waste problem.
And a cost-effective one at that. Natural resources are generally cheaper to source than their synthetic counterparts, making this process potentially more economically viable as well.
It's a win-win. So we've got our abundant natural catalyst. Now, let's talk about the plastic. This study didn't just investigate any plastic. They focused on some of the most common culprits clogging up our landfills. Polyethylene, polypropylene, and that notorious.
Polystyrene, the stuff of nightmares for environmentalists, or at least it was. It's known for its durability, which is great for, say, keeping your takeout warm.
But not so great when it comes to breaking down in the environment.
Exactly. Polystyrene can hang around for centuries. But in the context of this research, its durability might just be its saving grace. But we're getting ahead of ourselves. The researchers wanted to understand how efficiently these different plastics, polyethylene, polypropylene, and polystyrene, could be converted into fuel using this natural zeolite catalyst.
And here's where things get even more interesting. They didn't just use zeolite straight out of the ground, they gave it a little boost.
A boost in the form of modification. They tweaked the zeolite, enhancing its catalytic properties to squeeze every last drop of potential from this process.
Modified zeolite. It sounds like something out of a superhero movie. What exactly does it mean to modify zeolite, and why bother?
Think of it like this. You have a car, a perfectly good car. But you want to improve its performance, so you make some modifications. Maybe a new air filter, a better exhaust system. Modifying zeolite is similar.
So you're fine-tuning it? Getting it in tip-top shape for the task at hand?
Exactly. In this case, they used two main methods to modify the zeolite: acid treatment and thermal treatment, essentially exposing it to high temperatures. These treatments change the zeolite surface, making it even better at grabbing onto those plastic molecules and facilitating the pyrolysis reaction.
It's like giving those zeolite sponges a good scrub, making them even more absorbent.
The very scientific way of putting it. But you've got the right idea. So we've got our plastic villains, polyethylene, polypropylene, and polystyrene, and our souped-up zeolite hero. The stage is set, the heat is on, literally, and the pyrolysis process begins.
So what happened? Did the researchers just like throw the plastic and the zeolite in a giant oven and hope for the best?
Not quite. While the concept is based on heat, they use a highly controlled reactor system to simulate and study the pyrolysis process. It's all about precision and being able to carefully analyze the results.
Okay, so it's a bit more sophisticated than my kitchen oven. But the big question is, did it work? Did they manage to turn those plastic nasties into something useful?
Here's where the results get really interesting. They found that not all plastics are created equal when it comes to fuel production. Imagine that.
Oh, really? So some plastics are more eager to become fuel than others. Tell me more.
Well, polystyrene, remember that durable menace? It really stole the show. Yielded the highest amount of fuel compared to polyethylene and polypropylene. Who knew those takeaway containers had such potential?
That is fascinating. Is there a reason why polystyrene is such a fuel overachiever? Or is it just a happy coincidence?
It all boils down to its chemical structure. See, polystyrene is made up of these ring-shaped molecules called aromatic hydrocarbons. And guess what? Aromatic hydrocarbons are also key components of the fuels we use every day.
So it's like polystyrene is already halfway there.
Exactly. It's almost as if it's just itching to be transformed back into fuel. But it's not just about which plastic is the most willing participant. The researchers also found that the way they modified the zeolite played a significant role in the whole process.
Ah, right. The souped up zeolite. So how did those modifications affect the outcome?
Well, they discovered that treating the zeolite with acid rather than just heat made a world of difference, especially for our star performer, polystyrene.
So a touch of acid is the secret sauce. What's happening at the molecular level that makes this acid treatment so effective?
It's all about creating the perfect environment for the magic to happen. You see, treating the zeolite with acid changes its surface, creating these active sites. Think of them like docking stations specifically designed for the plastic molecules to latch onto.
So the acid creates these like molecular Velcro patches on the zeolite that the plastic just can't resist.
That's a great way to visualize it. These docking stations bring the plastic molecules into close contact with the catalyst, making it easier for them to break down during pyrolysis. It's all about increasing efficiency, ensuring those plastic molecules take the desired route towards becoming fuel.
It's incredible how such a tiny tweak, a bit of acid, can have such a big impact on the whole process. So the researchers have cranked up the heat, the zeolite is doing its thing, the plastic is breaking down. What happens next? We keep talking about this pyrolysis oil. What is it exactly?
Pyrolysis oil, also known as bio-oil, is the liquid gold we get from this process.
Liquid gold. So are we talking about something we can pour straight into our gas tanks?
Not so fast. While it has incredible potential, it's not quite ready to power your car just yet. It's more like a crude product that needs a bit of refining.
Crude, like crude oil.
Exactly. It's a complex mixture of different hydrocarbons. Think of it like a puzzle that needs to be pieced together. And to understand exactly what we're dealing with, the researchers use some pretty sophisticated techniques to analyze the composition of this oil.
Okay, so what did they find? What's actually in this pyrolysis oil? Give us the rundown.
They use techniques like GCMS and FTIR to break down the oil sample and identify its individual chemical components, kind of like giving it a fingerprint. And what they found was pretty exciting.
Lay it on me. What does the fingerprint of pyrolysis oil reveal?
A lot of those valuable aromatic hydrocarbons, remember those ring-shaped molecules we talked about earlier, the ones that make polystyrene such a good candidate for fuel? Well, they make up a significant portion of this pyrolysis oil.
So this isn't just any old oil. This is oil with real fuel potential.
You got it. And the research didn't stop there. They actually compared the energy content of this pyrolysis oil to conventional diesel.
Okay, and drum roll, how did it measure up?
It was remarkably close. This means with a bit of refining to remove impurities and meet the required standards, we could potentially be looking at a viable alternative to fossil fuels.
That's incredible. So we've tackled plastic waste. We're on the path to creating a new source of renewable fuel. Anything else? Any other surprises up this scientific sleeve?
Well, we've talked about the liquid gold, but this process also yields a solid byproduct, something called char.
Char, like burnt bits.
In a way, yes. But don't let the name fool you. This char is far from useless.
Char, huh? So we've got our liquid gold, the pyrolysis oil, and now we've got char. What do we do with that?
Well, it turns out this char is pretty remarkable stuff. It can be further processed to create activated carbon.
Activated carbon. Okay, I've definitely heard of that. It's in water filters, right?
Exactly. And air purifiers, too. Activated carbon is incredibly porous, giving it a huge surface area for trapping impurities.
So it's like a molecular magnet, playing out all the bad stuff.
You got it. Heavy metals, chemicals, you name it. It's used in a wide range of applications, from
Ugh.
cleaning up polluted water to removing toxins in medical treatments.
Wow. Okay, so not only can we potentially create fuel from plastic waste, but we can also get this incredibly useful activated carbon in the process. Talk about turning trash into treasure. It all sounds a bit like science fiction. So tell me, how close are we to actually seeing this kind of technology being used on a large scale? Are we going to start seeing like pyrolysis plants popping up all over the place?
That's the million-dollar question, isn't it? Well, the research is incredibly promising. We're not quite at the point of replacing all our gas stations with pyrolysis plants just yet. There are still some hurdles to overcome.
Hurdles. Like what?
Well, for starters, scaling up this process is a big one. The research we've been discussing was done in a controlled lab environment, using relatively small quantities of plastic. Scaling that up to handle the millions of tons of plastic waste generated globally, that's a whole other challenge.
Okay, so it's not just as simple as building a bigger reactor.
Not quite. It requires significant investment in infrastructure, technology, and research and development.
So it's a work in progress. But the good news is we're making progress. This research is pushing the boundaries of what's possible, and that's pretty exciting.
Absolutely. And it's not just about the technology itself. It's about changing how we think about plastic waste. It's about seeing those overflowing landfills not as a problem, but as a potential gold mine.
Turning trash into treasure, literally.
Exactly. And imagine the impact this could have, reducing our reliance on fossil fuels, tackling plastic pollution, creating new industries and jobs.
It's a vision worth striving for. And who knows, maybe one day soon those plastic bottles we toss in the recycling bin really will be powering our cars and cleaning our water. It's a future I'd love to see.
Me too. And the best part is, it's a future we can all be a part of creating.
That's a great point to end on. This isn't just about scientists and labs. It's about all of us making conscious choices, supporting sustainable technologies, and demanding change. So the next time you're faced with a mountain of plastic waste, don't despair. Think of the potential it holds, the fuel it could become, the resources we can reclaim. The solution to our plastic problem might just be right there in front of us, waiting to be unlocked. Until next time, keep those curiosity engines running.